what I want to talk about today is basically all the stuff that we didn't talk about, right? So I would call this further topics in machine learning. So basically, I look through my machine learning textbooks to try to find, okay, so what is the stuff that I could have talked about, but I didn't talk about? And I think actually, in the end, I was pretty happy with the amount of coverage I had. I think that in terms of learning basic machine learning theory, I think I did a pretty good coverage of all the stuff I think you might want to know. But there are many other things we could have talked about, right? And so what I want to talk about here is just maybe 5 minutes each on a bunch of different topics, just to give you an appetite for what more there is to say, right? So let's get into it. And these are in no particular order, right? So one thing is, in general, I would say there is a lot more to say on how do we actually do the optimization that is inside, modern machine learning algorithms, right? So, remember that kind of the setup for most of what we talked about was some sort of a, nonlinear cost function, right? Where we have something like this, right? Where there's like a ground truth y, and then we have a model based on some weights, right? So it's like saying this is kind of like our ground truth, and these are like the model, and the weights. I guess I usually use a red marker instead of a green marker. Okay. And so we know gradient descent, right? Gradient descent is most of what we talked about during the semester. So gradient descent would basically say that we update the weights by taking where we are now and taking a small step down the gradient of the cost function, right? But there are a lot more powerful ways of doing numerical optimization that we didn't talk about too much, right? And so some of these more powerful ways involve not just the first derivative or the gradient, but the second derivative, and that's what's called the Hessian, right? So there are, more powerful methods, and so some of these are called second order methods, and they involve what's called the Hessian matrix, which is basically the matrix of second partial derivatives against all the weights, right? And so instead of being if I have n weights, instead of being an n by 1 vector, I have an n by n square matrix that corresponds to this matrix of partial derivatives. And so if I had this matrix, for example, I could do something what's called the Newton-Raphson algorithm, which says that I update my weights by taking where I am now, taking a step in the direction of the Hessian inverse times the gradient, right? So this involves both the first derivative and the second derivative. So I think I actually alluded to this at some point. I remember talking about the Hessian and second order methods in one of the lectures. I couldn't remember which one. But there's a lot more to say about that. So in practice, computing this Hessian, this matrix of two second derivatives, can be time consuming for one thing, because instead of having to compute n numbers, I have to compute n squared numbers, or like 1/2 n squared numbers. And also, I'm actually, inverting that matrix. In practice, if you know anything about linear algebra, you know we probably should not be doing any explicit matrix inverses, but we still have to kind of compute some sort of representation of this inverse, right? And so there are different ways of, instead of computing this whole thing, you could do things like approximate this h by something that is simpler, right? So there are approximations that are called, for example, the Gauss-Newton method. There's something called the Levenberg-Marquardt method. you would learn about all this stuff if you took a nonlinear optimization class, right? So here at RPI, and I'm sure elsewhere, there are whole classes that are just based on teaching you all the different ways you can learn how to do optimization. So if you're interested in kind of the mechanics of how this works and what may be going on when you call a command in MATLAB or Python, then I was just taking a nonlinear optimization course. And that's, this is a pretty hand-wavy lecture. I'm not going to say any more about it. The other thing I would say is, there are some older methods that you don't hear so much about anymore, called things like, simulated annealing, genetic algorithms. You may see references to these things. So, these were basically, similar to how stochastic gradient descent randomly chooses which of the data points to use for each iteration. These older methods were also stochastic in nature, where they were kind of making some random choices about where to go next in the optimizer. So, these used to be more popular than they are now. You don't hear so much about these methods anymore, but if you read a machine learning textbook, you may see some references to them, right? So optimization is kind of like thing number one that, is kind of like a future topic, right? Okay, so thing number two. Thing number two, I would say, and I don't know why, I'm going to just adjust this a little bit. Whoa, hey, ho. Thing number two that I didn't say too much about, except in passing for SVMs and PCA, is more generally what are called kernel methods. Again, something that used to be super popular kind of prior to the advent of deep learning. So remember that, when we first started out talking about regression and classification, we were talking about, okay, I've got my raw data X, but I might want to transform that data into some sort of new feature space, right? Phi of X. So the idea was I have kind of like input data X, and then I apply some sort of a nonlinear function phi to get some sort of features, and then this is some sort of a, nonlinear function. And then maybe I use these phi to do regression or classification instead of just the raw features, right? And so that's very common. We did that when we were doing things like curve fitting. You used a polynomial basis, for example, as this set of phis, right? So the idea is that there was this thing that everyone started being excited about called the kernel trick. And the observation was that when you transformed your data into feature space, oftentimes you would see that the only way that your problem solution depended on phi was in a certain way, right? So, in many cases, the solution only depends on functions of the form like phi x1 transpose phi of x2 for two different sets of data points, right? And so the idea was that instead of specifying phi directly, we could just define what's called the kernel function k, which we set equal to this quantity, right? And so the advantage of just saying what this kernel function is that we don't actually have to form this potentially long vector of features. We just define a number that corresponds to what the kernel is between any 2 points, x1 and x2, right? So for example, you might choose a simple function like a Gaussian kernel, or I might choose something very, so if I just want to have a easy basis, I might say, okay, this is equal to x1 transpose x2. Or I might say it's equal to e to the minus 1 over 2 sigma squared, x1 minus x2 squared, or something like this, right? So the idea is I'm not specifying the nonlinear transformation at all. I'm just specifying the kernel, okay? And so this led to kind of so-called kernelized versions of linear things like PCA and support vector machines. Then there was kernel PCA and kernel support vector machines that were accomplished by bringing this kernel into the picture, okay? So again, something that was quite popular, I would say, a while ago, but not so much anymore. And there are lots of details about okay, so what requirements does this function have to satisfy in order to be kind of like a valid kernel? This also leads to things that are called Gaussian processes and so on. And so a good introduction to this topic would be found in a course like our Stochastic Signals and Systems course, right? So if you're a grad student, the Stochastic Signals course probably talks about kernel methods like this. At least that seems like where you would find it, okay? So there's more to talk about there, and we didn't talk about that too much. You're giving me, are you in that class right now?
Yeah, it doesn't talk a lot about kernels.
Right, okay. Well, it could talk about kernels. So, certainly more than I could. Okay, so that's one thing. Another thing I want to say that is an important topic in machine learning is graphical models, right? So, or probabilistic graphical models. So this is a fairly big topic. And so graphical models are a way of representing a complex set of conditional independences between a bunch of variables, right? So for example, let's suppose that we have some sort of a joint distribution, right? So I have 3 variables, A, B, and C, okay? And this is their joint PDF. So there are lots of ways I could break this joint PDF down using the laws of conditional probability. So for example, I know that I could write this like the probability of C given A and B times the probability of A and B. That's just the way that probability works, right? And then I could further break that down by saying, okay, I've got this conditional part, and then I could say this is like the probability of B given A times the probability of A, right? So this is just something that we could have done in our undergraduate level probability class, right? And graphical models are kind of a clever way of representing these relationships with a picture, right? So the picture basically says, okay, here there's a node that represents A, right? That's A by itself. And then there is a node B that depends on A. So I draw B, and I draw an arrow here that basically says that B depends on A. And then I have another node C, and C depends on both A and B. So I could draw something like this. And the idea is that here, for example, I have this network of relationships where A is the parent, and like B here is the child of A, and C is the child of A and B, right? And so if I had like more than 3 variables, if I had tons of variables, I can imagine I could have some sort of like super complicated, model with lots of nodes. Some are parents to others. Whoa, this is a big arrow, right? I'll draw a node there just to make it better, right? So the idea is that in some more complicated situation, maybe not all the nodes depend on all the other nodes, right? So for example, I could have a fully connected graph, or I could have a partially collected graph. I could have a cyclic graph, which means that if I were to follow these arrows around along where they're pointed, I could get back in a circle. In this case, this is not a cyclic graph, this is an acyclic graph, right? Usually that's what we want. And so overall, I could represent basically the probability distribution of any set of variables as the product over all of the possibilities of the conditional probability x of k given the parents of x of k. That's kind of what I did here, right? So like I took A, B, and C, and I decomposed it by saying, A doesn't have any parents, it's by itself. B, it only depends on A, and C depends on A and B, right? And so this is what's called a factorization of the joint PDF. And you can see it's not unique, right? Because I could have chosen, C to be the parents of A and B, and that would have been fine too, right? So there are different ways of factorizing a joint PDF. And these graphical models come up a lot in the context of things like information retrieval or databases or computer vision, places where, a piece of information depends on a few other pieces of information in the system, right? So I'm a computer vision guy, right? So for example, in computer vision, we might imagine that the random variables are the pixels in an image, and I kind of connect them up like this into a graph where the edges are basically just connecting local pixels together, right? And so in this case, what I might do is say, okay, well, the PDF of the entire set of pixels, I can think of it like a Markov type of independence, where it's like saying, well, this guy's PDF really only depends on its neighbors, right? Then you get something that's called like a Markov random field, right? So let's just say that, e.g., in computer vision, you might have what's called a Markov random field is one particular type of graphical model. And then in these graphical models, there are some kind of cool inference algorithms, right? So one cool algorithm that I didn't talk about in class, I thought about devoting a lecture to, but then I decided not to, is called belief propagation, right? So the idea is that, suppose that these are nodes that are in some sort of a complicated sensor network, right? And so maybe what I'm trying to do is, at my local node, I'm just trying to estimate my own PDF, right? Now I know that my PDF kind of is coupled to all the PDFs of the stuff around me, and so what I do is I design what's called a message passing algorithm, where I solicit input from all of my neighbors to say, hey, what do you think my PDF should be, right? So all my local neighbors pass some estimates over to me. I combine them with my own local estimate, and then I say, okay, well now I've got an update estimate. Now I'm going to tell you what I think that your, PDFs should be. And this kind of message passing process continues iteratively until everyone's converged to an estimate of what they think they should be, right? So in my early research days, I did a belief propagation algorithm for, calibrating a network of distributed cameras, and it's kind of a fun algorithm, right? And so let me just write down what that's called. Belief propagation, or BP, is a very common algorithm for graphical models. And so here at RPI, we have an entire class on probabilistic graphical models, right, taught by Professor G. So if you're interested in kind of like this kind of thing, again, there's a whole class on that, which is kind of why I didn't choose to have a whole, bunch of lectures on it, because it would overlap with that graphical models class, right? But knowing what you know here would be a good introduction to going to take that graphical models class. Okay, so another big topic that I could have devoted a whole lecture to is what are generally called sampling or Monte Carlo methods. And again, this is something that I may do next time I teach the course. I may have a whole lecture on sampling methods. So the basic idea here is, suppose we're doing some sort of system where we are building a, posterior distribution over some large number of variables, right? So for example, if we're doing generative modeling, we may have some, super complicated distribution of like, okay, here's the probability distribution of pictures of cats, right? So like, it's a really weird kind of complicated distribution to describe over all the possible sets of images, right? So the idea is that, we have a, difficult to evaluate, posterior distribution. P of z, so let's say. And we want to compute some sort of expected value of a function according to, P of z. So, maybe I have some function as like how fuzzy the cat is, right? So I want to find the expected fuzziness of the cat over the whole distribution of cats. Well, this may not be so easy to do, right? In practice, what we do is we sample from the distribution, and then we evaluate this expected value basically empirically, right? We basically say that, we take the expected value of this thing is approximated by the average of a bunch of samples here, where these zi are basically, identically distributed samples from P of z, right? So it's easy for me to generate a cat picture, right, with some generative algorithm, but it's not easy for me to describe what the whole distribution over cat pictures looks like, is the idea. So it's easy for me to generate samples, but not possible to evaluate this entire distribution in an easy way. But there are lots of problems with this technique, right? It has to do with like, how many samples should I take of the distribution and where should I take them, right? So for example, let's suppose that kind of in a very sketchy way under the hood, the P of z looks like, this, where it's big in some places and small in other places. And then let's suppose that the function that I'm trying to evaluate looks like, like this, right? Well, the problem is that if I'm sampling according to the underlying P of z, then I'm going to get very few samples that are over here and lots of samples that are over here, right? But the thing that I actually care about, this red function, actually is pretty small over here, and it's pretty large in places where things are not well sampled, right? So let's just say that here, this is kind of like saying, you know, rarely sampled, but big values. So there's a question about like, okay, you know, how much do I have to sample in order to be sure that I've gotten a good coverage of where the function, you know, where the function may be active, right? So there are lots and lots of ways of doing this in a clever way. And so if you took probability with me, at the very end of probability, we talked about how do you sample from a PDF, right? So there are a bunch of methods, right? There's like this method where you take the CDF of the random variable and you generate a uniform random variable, you follow it over to the CDF and you follow it down. That's great when you can characterize the PDF of the thing that you care about explicitly. If you can't do that, then you can kind of draw the PDF, and there's something called the rejection method where you basically throw darts at the PDF, and if you fall into the curve, then you accept the sample, and if you don't, you keep on throwing darts until you do, right? So you can think about rejection method sampling for something like this, but there are smarter ways to do it, and one way that is very common is what's called importance sampling. So, importance sampling, let me see here. So, importance sampling, the idea there is that we have kind of like what's called a proxy or a proposal distribution, Q of z, which is easier to sample from. So like suppose that we just approximate this here by some other proposal distribution, like a Gaussian. And then there's kind of like a complex set of, okay, it's easy to sample from this proposal distribution, but then I need to know how do I change that result to match up with the underlying P of z. So there's a process called, there's basically a process of weighting the output of F of z in a way that is fairer to make something that approximates what P of z is, right? So there's a whole bunch of like, variations on this theme. So for example, if you look at a machine learning textbook, you'll see things like something called Metropolis Hastings sampling, or Markov chain Monte Carlo, MCMC is a very popular way of sampling. And so kind of the idea is that what you're doing is you're generating new samples based on what you saw before. So it's like saying that we create the next proposal distribution based on the current sample. So you basically have something that's like a Q of z that depends on the previous thing that I came up with. And then you sample from that and you accept or reject the sample. And the sequence of samples that you obtain form a Markov chain, because what you're doing now depends on only what you did in the previous step, right? And so it's similar to what we talked about for hidden Markov models, right? There's kind of a relationship between stepping between the states of a Markov chain and this kind of process here, right? And so again, there's lots of details on how to make this sampling process work. And like I said, I didn't really talk about it too much because I'm not like super jazzed about this kind of material, so I just feel like I don't want to talk to this. But if I had one more lecture in this class, I might have one that's devoted to sampling methods by itself. If you look at the original syllabus, you can see that's what I was thinking about doing today, but then I decided to just kind of do this like bigger picture lecture. But if you look at like Bishop chapter 11, there's a ton of details on exactly how many samples you need, how you create the proposal distributions, how you weight the proposals, and so on, right? So there's lots more to say about that. Okay, so there is a whole other bigger picture that I feel like, for example, if you took like Malik's machine learning class in computer science, I feel like some machine learning classes are much more emphasis on kind of like the theory, the big picture of like what learning is possible, right? So like there's kind of like this big picture of, what can be learned, like fundamental limits and boundaries of machine learning, fundamental theories of machine learning that are not really tied to any particular algorithm, but are more big picture, right? And so one question we could ask is, is one algorithm so in this class I taught you like a whole bunch of classification algorithms, a whole bunch of regression algorithms, right? So is one algorithm just like uniformly better than all the other algorithms, or than some other algorithm? If I have algorithm A and algorithm B, can I conclusively say that yes, algorithm A is just better in all cases than algorithm B, so we don't talk about algorithm B anymore? The problem with that is that there are some fundamental machine learning theories that say that no algorithm, when operated on totally unseen data, can be any better across the board of all possible problems than any other algorithm. So basically, there's a theorem called the no free lunch theorem, which in a very kind of slangy way says that, uniformly averaged over all, possible target functions f, right? So suppose we're solving, a classification problem. Maybe this f is basically all the possible ways in which a set of points could be classified, right? So uniformly averaged over all the possible problems that I could solve, the expected off-training set error for all learning algorithms is the same. Right? No matter how clever you are, how great your algorithm is, in the end of the day, if I were to look at an average across all the possible problems that I could pose, there's going to be at least one problem where just randomly guessing the answer is going to be better than whatever your classification algorithm does, right? So it's a little bit easier to see in a graphical way, right? So for example, let's suppose that this box represents all of the possible problems that I could solve, like all the possible classification problems I could solve. And I'm comparing two algorithms, A versus B, and I'm going to make a plus sign that says that A is better, or a minus sign that says A is worse, right? So it could have a situation like this, where there's a whole bunch of problems for which A is much, much better than B, but there are a lot of problems where A is a little bit worse than B, right? So on the average, over the whole problem class, I have basically 0, right? There's a wash. Or I could have something like this that says, okay, there are some problems where, on this side of the line, A is better, on this side of the line, B is better, but everything kind of averages out. Or I could have a situation like this, where it's like, there's a whole bunch of problems where A is, better here, and A is worse here, and then I have, all these places, A and B are about the same. So the no free lunch theorem says any of these things is okay, because kind of the average over the entire square is still 0, right? There's no net gain of algorithm A over algorithm B. What I can't have, so these are basically all, these are all possible, right? What's not possible is something like this, where, across the entire domain of problems, A is just better everywhere, right? Or A is better over here, and everywhere else it's, about the same, right? This would mean that there was a conclusive net gain or net better result for A, right? So it seems counterintuitive, right, that this is true, but this is, again, one of these kind of fundamental theorems of machine learning. And so, I think it's okay. I'm not really into the limits of machine learning, but this is one thing we could have actually started class talking about before we even got into any sort of algorithms. We could have talked about kind of like the limits of machine learning. And so this is kind of related in some sense to, we didn't talk too much about like model selection, right? So this kind of gets to the question about like, okay, so is there any reason to prefer one algorithm to another, right? If they're all fundamentally the same. Then it comes down to things like, okay, so I want my model to be less complicated, for example, right? So this is related to algorithms for model selection. So remember on one of the homeworks, I asked you to do something called the Bayesian information criterion, I think, when you were choosing, for example, how many Gaussians to use in a Gaussian mixture model. There's something called the BIC. There's also something called the AIC, which stands for the Aikake information criterion. There's something called minimum description length, MDL. So again, if you read a textbook, you'll see these things. These are all kind of related to kind of like you have your performance, so your accuracy, plus some weight times the model complexity. That's kind of like the philosophy behind all of these kind of model selection algorithms, where this is like the number of parameters of the model, for example. And then there's also something that I really remember liking in my machine learning course when I took it like 25 years ago. Again, I didn't think it was worth a whole lecture, but there's basically something called the VC dimension, which stands for Vapnik-Chervonenkis. And so this basically relates to kind of like, we were talking about kind of bias variance trade-off. We talked about that earlier in the lectures, right? And so the VC dimension is kind of related to the classification ability of a given class of models. It basically says how wiggly is my classification boundary able to get. And so there's a cool idea in VC dimension called shattering. The idea is that if I have like a set of 3 points here, no matter how I label these 3 points with X's and O's, like so for example, say that I call these X's and I call this one O, I can always draw a single straight line that divides the X's from the O's, no matter how these 3 points are labeled, right? So what this means is that a straight line can perfectly shatter these 3 points, right? However, if I had a different situation like this, say I had X's and O's, or say I had points like this, a straight line cannot shatter these 4 points because, maybe if these were labeled X's and these were labeled O's, I could draw this line. But if I have something like this where, this is labeled X and these are labeled O, then there is no straight line that divides the X's from the O's, right? So I can't shatter, these 4 points, but a nonlinear function could, right? So I could choose, for example, a polynomial that would kind of loop around and divide the X's from the O's. And so there's definitely interesting theory to be talked about in terms of, how much can a certain class of functions do. So again, kind of interesting, but also kind of like abstract and theoretical, right? So I guess I don't know how much of this they talk about in the other machine learning class, but I decided to err more on the side of practicality when I taught this class. Okay, so one other big debate, which again I could have talked a lot about in the beginning of class, which I didn't, is kind of like frequentist versus Bayesian. I guess I can't let you get out of this class without talking a little bit about what this means. So there is a huge philosophical division in the machine learning world between people who are frequentists and people who are Bayesians, right? And so kind of the difference is between people who are more statisticians and people who are more like, I wouldn't say engineers, but more kind of like probability people, okay? So to kind of divide this into, what does this mean? So the frequentist philosophy is basically, only, look at the data, right? So this is very dominant in many fields, like medical, testing, social science, anywhere where you're reading a paper and you see like confidence intervals and p-values, that's all a frequentist kind of world, right? Where you look at the data and you build tables of things. And there's a lot of, so what is a p-value? It's kind of like saying, okay, what's the probability that a data set that is this extreme could have happened by chance, right? The Bayesian philosophy is basically, to consider priors on the parameters of your model. Right? So we talked about regularization, right? To say, okay, the reason why we may include a little step that says lambda times, the norm of W is that we have a prior belief that the weights should be small, right? Or we may have a prior belief that the weights should be Gaussian distributed around 0. For example, we have a probability model for the parameters, right? And so kind of like, everything that the Bayesians do stems from Bayes' rule and Bayes' theorem, right? Which is one of the first things we talk about in probability. And so it's definitely true that Bishop, the author of the book, for example, is a Bayesian, right? Because I think it's, every chapter concludes with like, okay, if we were to put a Bayesian model on the parameters of this, how would it look, right? I didn't make a big emphasis about like frequentist versus Bayesian. We do talk about that. I mean, it's basically the difference between maximum likelihood estimation, which happens a lot in machine learning, and map estimation or maximum a posteriori information, which comes from having some sort of model over my parameters, right? And so a frequentist would never be happy with the idea of bringing in some sort of external priors on the parameters, right? That's something that's like, okay, you're going outside of the data, and the data is the only thing we have to work with. That's the frequentist world. And so that's kind of like the fundamental worldview difference. Some people get really worked up about it. I don't really get worked up about it, but it's something that you should know about, I guess. In the frequentist world, again, we don't really have a statistics like department here, but like, for example, the difference between Bayesian and frequentist in some sense is like the difference between Mao and engineering probability, right? So engineering probability is all about Bayes' rule, and Mao is all about like looking at tables of data, right? So it's kind of like the difference. So if you were a statistician, you would learn about there are these things that only depend on kind of resampling the data in different clever ways, right? So there's something called the bootstrap and the jackknife and these kind of cool looking things. These are all things that are kind of more statistical in nature, okay? And then also in a statistics class, you may talk more about things like, curve fitting and splines and so on, where you're kind of like fitting, things just to the data. There's more you could talk about with that. So anyway, I think that the main difference is that, the key difference is are the model parameters random variables? If you say no, you're a frequentist. If you say yes, you're a Bayesian. That's kind of what it comes down to. Okay, so I think that is a pretty good coverage of the stuff that I thought that I might have spent a lecture on, although seeing it now, I'm not sure what I would expand into a whole lecture. I could certainly have a whole lecture on graphical models. I could have a whole lecture on sampling methods, and so in a future class, I may do that. And actually, that's one of the questions on the course evaluations is, okay, so what more would you have liked to have seen me talk about? With the caveat that we have all these other classes that go into machine learning in more depth, right? We could certainly talk a lot more about reinforcement learning, for example. We have a whole class on reinforcement learning. We talk more about, partially observable Markov decision processes. We have a class on that. We have a class on graphical models. So this is, again, meant to be just like, a broad overview of key machine learning terminology. So that's something to think about. The last thing I want to say is, as a warning, I guess, is that, one of the first things we talked about was the curse of dimensionality, which is that things are hard to reason about from pictures or from kind of like mental models alone, the more data you have. And of course, in our world, we have so much data in these big, large language models and generative algorithms that it's really impossible to get a handle on what your data looks like. But sometimes that can be really important, right? So kind of, this is an example of what's called Anscombe's quartet, right? So we basically have, like a dozen data points. 1, 2, 3, 4 are the classes. The data points are on the left. And these 4 classes of data all have exactly the same mean in X and Y, exactly the same variance in X and Y, exactly the same correlation, and exactly the same kind of like linear regression line. But if you actually look at the data itself is wildly different looking, right? So like the data set number 1 is kind of like data set number 1 is kind of like what you'd expect, I think, as, this is like a straight line fit to some data. But the same straight line fits this weird curvy data. You'd say, okay, if I looked at this data, I think this is better as a quadratic problem, for example. This, you'd say, okay, well, this is a problem where I have to do some sort of outlier rejection before I fit my line. And this is like saying, well, here, there's a straight line here, and there's one data point that throws the whole thing off, which again is a problem with linear regression. So kind of the upshot is that without looking at your data, in some way, it's very difficult to reason about it, right? And so someone also took this to a fun extreme, and they created what was called the Datasaurus dozen, which has got basically these sets of points, again, have the same means and variances and regressions, except they all look wildly different, right? Sometimes the line's going this way, one of them looks like a star, one of them looks like a dinosaur, right? One of them looks like a circle, but these have all the same kind of like base level statistics. And so this is called the Datasaurus dozen. And so I don't want to give to you Wikipedia. Sorry, I love you, but no. And so again, this is kind of like saying that they all have the same regression. It's basically the same kind of deal, right? And so someone had fun making the dinosaur. And so this is probably also built into stuff like Python and so on. So again, I know it's not very prescriptive when it comes to your own problems. But again, I am a big believer in not just looking at the raw number that comes out of PyTorch and saying, oh, my algorithm is better than this algorithm, right? There are lots of considerations, and looking at how these, looking at your data in 2D slices, for example, or 3D slices is sometimes very handy. We talked about this algorithm called Tisney, for example, which is a way of visualizing how data is clustered. That's a good thing to do. And last time we talked about also a whole bunch of different, or maybe it was the time before, we talked a whole bunch of different ways to evaluate data in different ways, right? And so don't just try to boil your problem down to a single number, I guess is my final word of wisdom to you. All right, let me stop and ask. Any questions or comments about any of the stuff I just said? All right, so I'm going to stop the lecture.